Okay, so picking up where we left off yesterday, we have one little thing to talk about before we get into the conservation of energy, and that is the idea of heat. So we're actually going to spend a ton of time in January talking about heat when we do our thermodynamics unit. But for now, we're going to have a simplified definition of heat here. So we're going to say that heat is a change in energy, much like work, but heat's a change in energy that results from energy loss, typically from friction or sound or things like that when objects collide. All right, so whenever objects are losing energy, which is constantly happening in real life, whether it's air resistance or friction or collisions or whatever, that energy is going to heat. Okay, and heat actually is where most energy ends up, to be perfectly honest with you. That's kind of like the ultimate destination for energy as it becomes heat. But like I said, we will study this much more in depth later in the year. Okay, moving on here to the big idea, which is really conservation of energy. So, conservation of energy tells us that the total amount of energy in the universe is constant. If we added up all the energy of all the objects in the entire universe, that number has not changed. It will be the same number tomorrow, it will be the same number 5 days from now, it will be the same number 10 years from now. The fancy way of saying this that you'll often hear is that energy is neither created nor destroyed, it only changes forms. And that really is why energy is such a powerful tool, is because the total energy of the universe is conserved. It is important to note, though, that the total energy of the universe might be conserved, but specific individual objects can gain or lose energy. And we're going to talk about how we're going to analyze objects gaining or losing energy in the problems that we're going to do today. Let's talk now about how conservation of energy applies to individual objects, because as we said in the last slide, those objects can gain or lose energy. So there's two circumstances when objects would gain or lose energy. The first is energy transfers from one form to another within the object. In this case, total energy is unchanged. This would be your classic example of an object falling maybe, and its gravitational potential energy is becoming kinetic, or something along those lines, where we go from one form of energy, gravitational potential, whatever, to another form. The second way that an object can change its energy is through work. Okay, we talked before about how work is the change in energy that results from a force. So when objects exert forces on each other, and they always will because of Newton's third law, we can have a transfer of energy via those forces. All right, so in that sense, when there's work being done, energy actually transfers from one object to another. The energy of the universe stays the same because one gains energy while the other loses energy, but the energy of the individual object does change when we have work being done. So we see here two examples with numbers written out. First we have this gentleman diving off of a platform into a bucket. Can't see how that could go wrong. Starting off with 1,000 joules of gravitational potential energy. As he falls, that gravitational potential energy is decreasing and becoming kinetic. We see here at the halfway point, we're down to 500 of each, but we notice that the total here still remains 1,000 joules. We continue to fall, and we eventually reach this bucket, and at that point, all of our energy has become kinetic. So this 1,000 has slowly been transferred to all kinetic energy. So that's situation one, changing the type of energy within an object. Our other situation, when we have work being done on an object leading to a change in energy, would be this case here with this gentleman pushing the wooden box. We start out with the box at rest, so it has 0 joules of kinetic energy, and we exert a force on it, doing work on the box, giving it kinetic energy. So that's an example of work allowing energy to be transferred from one object, in this case the person, to another object, in this case the box, through that force, through work being done. That work case is a really important form because the only way for the total energy of an object to change is through work. Now, technically, that's the only way for the total mechanical energy to change. We'll talk about energy changes that result from heat much more in depth in our thermodynamics unit. But for now, the only way for the total energy of an object to change is through work. That concept, that's a really, really key concept. And that's going to allow us to analyze a variety of situations. And the reason why it does that is if we know the initial energy that an object has, okay, and we also know the amount of work done on that object, we can easily find the final energy of that object. And that right there is a really, really powerful tool. From an equation standpoint, this is that concept we were just talking about in equation form. The initial energy of an object, okay, that's what we're starting with, plus any work done is equal to the final energy of that object. We will talk about the NC in 1 second. It stands for non-conservative. I do want to point out, you might have seen this slightly differently last year, depending on who you have. You might have had something along the lines of KE plus PE initial equals KE final plus PE final. That is one other way of writing this equation. Similar to momentum, I don't like to write out the full equation with everything already added in there. What I like to do, and we'll see this when we do some sample problems, is really think about what kind of energy do we start with, is there work being done, and what kind of energy do we end with, and kind of creating our own equation that describes each situation. But different people have different preferences, and if you would rather do it a different way, that obviously is okay. Let's talk about that NC piece for a second, because you probably noticed on the previous equation we were talking about work NC. So the NC stands for non-conservative. And the reason why that matters is only the work done by non-conservative forces will actually change the energy. So what exactly does that mean? Well, we have two forces really that we care about. The first is gravity. The second is spring forces. And those forces are considered conservative forces, and here's why. Imagine we have an object, okay, that's traveling upward with some velocity. We would say it has kinetic energy. And that object's going to rise up to the peak and eventually reach its maximum height, where it has zero velocity and therefore zero kinetic energy. So if we think about that situation as that object's rising to the peak, okay, we could say that work is done by gravity. And that would be a perfectly correct statement to say that work is done by gravity. All right? Object's rising, it starts with kinetic energy down here, and it's losing its kinetic energy because gravity's doing work. However, once it gets to the peak, it's going to fall back down. And all of that energy that it initially had, it's going to get back. So it rises to the peak, gravity takes away its kinetic energy, and then it falls back down, and it gets that kinetic energy back as it's falling back down. And so that work done can be undone, okay? And that's really the key qualification for something to be a conservative force, is can that work done be undone? And we see the same thing with springs, okay? If we have an object moving, it runs into a spring, it compresses the spring and eventually takes away the kinetic energy of the object. But what can happen then is that spring will uncompress and will give the object back its kinetic energy. So that's another example of a conservative force. All right, the spring takes away the energy, stores it temporarily, hence it being called potential energy, and then gives it back. All right, so both spring and gravity are potential or are conservative forces. And when we have conservative forces, right, they don't actually change the energy of the object. We instead say that that energy is simply being stored as potential energy. All right, it's not that the force did work and took energy away. That energy was just stored as potential energy. So if that was a long explanation that you don't feel like remembering, what you can remember, the shortcut is simply that gravity and spring forces are conservative forces. And those are the only conservative forces that we're going to deal with for now. Okay, so if gravity and springs are conservative forces, what are non-conservative forces? Well, the major ones we're going to talk about are friction, pushes, and pulls. These are all examples of non-conservative forces. And the reason for that is that these are permanent changes to the energy of the object. Okay, if we have a box, for example, sliding to the right across the level surface, and there's a force of friction acting on that box may start out with kinetic energy, but eventually at some point in time later, it's going to come to a stop, and it's going to have zero kinetic energy. And what we would say is that in that case, work was done by friction, and that work took away the kinetic energy of the object. However, unlike the gravity situation that we were just talking about, this cannot be undone. Okay? This actually changed the energy of the object. It actually took energy away from the object, and we're not going to get that energy back, right? You've never in your life seen a box sliding across the floor, slowing down to a stop because of friction, and then magically sliding backwards. That would be weird. That doesn't make sense, okay? That work done by friction cannot be undone. And so we don't say that that energy became potential. We say that work was done by a non-conservative force. It took away the energy of the object. And the same thing with pushes and pulls. If you push something and you give it energy, you can't take that energy back. There's no way to undo that transfer of energy, to undo that work. So that's the key distinction. Once again, if you just remember friction, pushes, and pulls, those are our examples, our primary examples of non-conservative forces. That's fine, but I do want to give you the more thorough explanation. Okay, moving on to a few tips here for solving these. We're starting with that equation with our E initial plus work done by non-conservative forces equals E final. We're basically going through and filling in each part. So what kind of energy do we start with? What kind of energy do we end with? And is there any work done by non-conservative forces? All right. And so we're really going to make our own equation that describes the specific situation that we're given. So here's our first practice problem. We have a Nerf gun or a Nerf dart fired straight up in the air using a spring-loaded gun. So I'm first going to think about my equation, and I'm also going to draw a little diagram showing the energy that I have and at what points in time I have that energy. So what kind of energy do we start with? Well, initially we know that the gun is spring-loaded, so that means we're starting out with gravity or spring potential energy. The object's not moving, so there's no kinetic, and there's no height. All right. A quick note about height: we can always set our height equals 0 point to be whatever we want. There is no absolute zero height point. Okay. So what I typically do is just say that the lowest height in the problem is our 0 point and measure everything based off of that. So our only energy that we have to begin with is this spring potential energy. Moving on, is there any work being done? So we're ignoring frictional forces. All right, so that's out for any work being done. The force that actually launches it here is a spring force, which is a conservative force, so that is also out as being work done by a non-conservative. So there is no work done by a non-conservative force in this case. And this is going to equal our final energy. So we're thinking about up here at the peak, okay, at that maximum height. What kind of energy do we have? Well, we have gravitational potential energy, clearly, because we have a height. We don't actually have any kinetic energy, though, because we remember when something is at the peak, our velocity is 0. So we're ending here with just gravitational potential energy. This is really the key here, ladies and gentlemen, is looking at this problem, looking at that wording, and translating it into types of energy. Okay? And really what it comes down to is there a spring, in which case it has spring potential energy? Is there a height, in which case it has gravitational potential energy? And is it moving? Okay, in which case it would have kinetic. But in this case, we end with just purely gravitational potential, no kinetic. One other quick note, some of you might make the point that we have kinetic in between, and that's absolutely true. We actually have spring potential energy becoming kinetic in between before eventually all of it is transferred to gravitational potential. We don't need to account for the kinetic at all. As long as we correctly identify our initial energy, correctly identify our final energy, it actually doesn't matter what happens in between. The only thing we're concerned with in between is any work being done. And in this case, that's 0. All right, so we've dealt with all the in-between part. It doesn't matter that it goes from spring to kinetic to gravitational potential. We can just say it starts with spring and ultimately goes to gravitational potential, and that's all that matters. Now that I have my basic equation, I'm going to start filling in the things that I know. I know spring potential energy is 1/2 kx squared. I know gravitational potential energy is mgh. So I'm going to plug in the numbers I know here. So there we have it. That left side is going to be 2500. That's my spring constant here. My x, my distance stretched to compressed, is 7 centimeters, but we need to convert that to meters, which is 0.07 meters, which is why I'm plugging that in right there. My mass I know is this 0.3 here. I know 9.8, of course, and I'm looking for my height. So I go ahead and do some math here. I find this left side becomes 13.475 equals 2.94h. And so my height here becomes 4.58 meters. Okay, moving on to the next one here. Once again, I'm going to start with my basic equation that energy initial plus work done by non-conservative forces equals my final energy. So the first thing I'm going to do here is I'm simply going to identify the energies that I have at various points in time. So at A, we have a height above the ground. So I'm going to say UG in this case. And we have a kinetic energy because we are moving at a given speed at that time as well. At point B, I have a height above the ground, so that means I have gravitational potential energy. I'm also looking for how fast is it traveling now. So that means I have kinetic energy too. For this problem, I am saying that my height equals 0 is down at the bottom here, and that's simply because that's how the problem was written. It already defined that for me. I could ultimately solve for it, but that's probably more work. So what I'm going to do now is start filling in my equation. So I'm going to say I start with UG plus K. I don't see anything about work being done. I'm ignoring friction here, so there's no work done by friction. Gravity is a conservative force, so there's no work done by a non-conservative force there. All right. So in this case, once again, my work done is 0, and I end here with gravitational potential energy and kinetic. The one thing I'm going to do is I'm going to add little subscripts here. I'm going to call those both I for initial and these both F for final, just so we don't get them confused. Next, I'm going to fill in the equations I know here. So I have mgh initial plus 1/2 mv initial squared, and that's going to be equal to mgh final plus 1/2 mv final squared. Once again, I'm going to fill in the numbers that I know here. Alright, so filling in the things I know, I'm starting at an initial height of 1.5. I don't know my mass, so I'm just leaving that as a blank. I know my initial velocity is this 1 here, right? So I fill that in, once again leaving my mass as a blank. And at the end, I have a height here of 0.8, and I'm looking for this final velocity here. So obviously that's going to still be a unknown. So we notice that we don't actually have the mass. However, that mass does appear in every single term. And so what that means is, because the mass is in every single term, that mass will divide out. Okay, and so what I'm left with here is 14.7 plus 0.5 is going to be equal to 7.84 plus 1/2 VF squared. So when I add these two numbers here and subtract that 7.84, I'm left with 7.36 on this side equals 1/2 V squared. Dividing by 1/2, I get 14.72 equals V squared, and that, in this case, is that final velocity at the end. And so when I solve for VF, I get 3.8 meters per second.